Mic check, mic check. Good evening, everybody. Sorry, I almost said good morning. My name is Cedric, and I am joined by the wonderful Carol Chen, and we're excited today to be, hopefully, talking about bootable containers. I've dropped this laptop a lot of times, and I'm due for a refresh. Let's see if we can get it back off. Thank you. Yeah, I'm like cursed. Knock on wood. So, but thank you all for being here. We've got a lot to talk about today because a lot has happened in the past year, and some stuff that you might have known or heard about, for example, was talked about at KubeCon this year, where we had the, Last year. This, yeah. November 4th. This man knows. Oh. Okay, so last year, where at KubeCon there was a big announcement to donate some projects that we'll talk about here in a second to the Cloud Native Computing Foundation, one of which was accepted last week that we're going to be talking about today, bootable containers. Now, what are bootable containers? Well, this is primarily the topic of the session's topic, right? What the innovation is and how you can actually use it, and we're going to do some hands-on demos today with Podman Desktop, an open source tool that was also donated to the CNCF to package up and experiment with AI applications and be able to deploy them as OSs using bootable containers as a technology, so that you can take all of your traditional build processes, CI/CD testing and verification of cloud native applications and apply that to disk images as well and be able to deploy them wherever you deploy your applications. And that's why Podman Desktop is involved, where we're going to be showing the demo today. So if you'd like to take a look at the slides or the code that we're going to be using today in the demo, feel free to check it out here. We've got this also included on the conference schedule, so if you go later on to the CentOS Connect website, check out this session, you can download the PDF for the slides as well. So without further ado, we ready to hop in? Awesome. Cool. I'll do a quick introduction for myself. Hi, my name is Cedric. I'm a first-time attendee for both CentOS Connect and FOSDEM. It's crazy. Thank you for the woo. I make videos on the internet, so for example, you see one of those RAG versus fine-tuning that I did with IBM, but I also just make content for developers to learn. I'm an application developer myself, and I dive into containers and AI topics, and I create workshops and demos, and I'm also an organizer for the KCD Kubernetes event in New York City, where I live, and a speaker at some other Linux Foundation events, and pass it over to the wonderful Carol.
Thanks, Cedric. Whoa, this is loud. I'm Carol Chen from Red Hat. I'm a AI community architect, or a community architect in general. I've had the pleasure of leading and supporting many different projects since working in Red Hat, and actually also outside of Red Hat and before Red Hat. So here's just some of them. You might recognize some of these projects. I'm a bit more camera shy, so I don't do a lot of videos like Cedric does, but you know, I really appreciate people who can take interesting technical topics and bring them and explain them to be accessible to a lot of people. So great work, Cedric. Yeah. And if you want to look for me online on the usual haunts, nowadays I don't hang out on X too much, but Mastodon, GitHub, Matrix, that's my Matrix ID, and Blue Sky, you can all use the @SciBat ID to look for me there.
Awesome. So go ahead and kick it off with one more plug, just quickly for, who here knows Dan Walsh? Familiar with his work? SC Linux fans or haters? If you want to check this out, I produce a show with him. It's called Red Hat Dan on Tech on the YouTube, and we cover all types of topics: SC Linux, containers, Podman, tooling, Ramalama, which is the new tool for AI to run it on your local machine, systemd, Quadlet, etc., etc. If you want to learn about the people behind the projects, I highly recommend you check out the show. Episodes are like 10, 15 minutes, and we do deep dives and demos on all of these different technologies. So, quick little plug. Carol, question for you. The question of the day, question of the session. What are bootable containers, and why do they matter, and what do they solve?
Wow, that's a good question. And I recently just learned about bootable containers myself, so hopefully I can be able to shed some light of what I've learned with all of you. Now, imagine deploying your entire operating system with the same ease and consistency as your applications, containerized applications. So bootable containers are what makes this possible, because it unifies system deployment and application management into a seamless, efficient process. What do I mean by that? Oh, all right. Thanks for advancing the slides for me. So for the most part, when we talk about operating systems, it seems like it's a solved problem, but if we look closer, we realize there are a number of things, a number of challenges where people and organizations, when they intersect with technology, depending on your company or industry, some of these could be some challenges that you face. So oftentimes, different platforms tend to require different tooling, or you have to find expertise for very specific platforms for your organization. So while that isn't necessarily a problem in itself, there's inherent overhead and complexity that requires more coordination, and with that, it impacts velocity, the speed that you're moving with your organization or company. So another thing is for testing and validation, a lot of times in practice, budget don't really factor in like maintenance costs, upgrades of the OS, and also the applications running on top. Patching stuff may be easy, but negotiating downtime with stakeholders and different teams involved can be difficult and time-consuming. So these are just some of the hurdles that when we come to the operating system, you may not have ready easy solutions. So let's see how bootable containers can address some of these. And actually, before we go into bootable containers, let's talk about containers. So if we look at the application side of things, containers solve some of these problems that I mentioned. In terms of like packaging, delivery, they are kind of pretty standardized because the adoption of containers has been pretty fast. Well, over the last 10 years, but it has been used in a lot of places, very much standardized compared to the previous virtualization and cloud computing waves. So this has really a profound impact on the way that people share and use applications with containers. The key lesson here is that containerization technologies and workflows provide just enough standardization, structure, and ease of use. Containers are becoming ubiquitous, and you can build them anywhere. You can do it in production, you can scale it up using pipelines, or even independently on your laptop. It's fast, and that's really, these building blocks of containers has spurred a whole ecosystem, Kubernetes and all the different tools around it. So, oops, how do I go? Yeah, okay. So the earlier mentioned problems have been solved in the application space, and now we're going to apply it to the operating system space. I think with containers, this next step is like a natural evolution to bootable containers. So for over a decade now, containers have evolved into this industry standard. So bootable containers build on top of these existing technologies and extend containers to the entire operating system. And includes also the Linux kernel, like you see here, to allow for a comprehensive container-native workflow and user experience. This is just a simplified illustration, but it basically includes and ships the whole entire OS, includes the kernel, bootloader, and drivers. The ultimate goal here is to install the whole content of this bootable container image on a host. Updates to the host are also applied via bootable container images. So this means that we pull updates from a standard container registry, as we did with the application containers, the usual way. So let's have a closer look of what this means and how the process looks like. As you know, OCI containers have become the de facto way of deploying and completing a Linux user space for applications. A large set of practices and tooling have evolved around that. Bootable containers are a modern, opinionated way of deploying, configuring, and managing immutable image-based Linux systems using these practices and tooling. So just like ordinary application containers, you can build bootable containers by using existing container technology, such as container files, including Docker files, and with existing tooling such as Podman, Docker, or BuildKit. You can further store these images on any container registry. Example, Quay, Docker Hub, GitHub container registry, or even some internal container registries that you might have. All right, let's look at how to deploy and update a system. So this figure shows the life cycle of a bootable container and the different steps from building to deploying and updating the system. So from a container image, if you might notice, I actually have my speaker notes in my glasses. Anyway, once a container image has been built, it needs to be converted to a disk image, such as ISO, RAW, or QCOL2. This disk image can then be installed for some target environment, which can be a public cloud instance. You might also want to push the container image to the container registry that you choose. And that's to deploy a new image. To update existing systems, you also build this image to be updated and push it to the registry. Once that's pushed there, the deployed systems on the right can then pull the new image from the registry and then reboot into the new image for the update. All right, what are the tooling involved in this bootable containers? So bootc, that's at the core and center of the bootable containers. It is a command line tool that ships with a number of systemd, services, and timers to manage the bootable container. And among other things, bootc is responsible for downloading and queuing updates and can be used by higher level tools to manage the system and so on. For this reason, bootc is an integral part of each bootable container image. And there are several ways how an individual system can be updated, including by default is the time-based updates with systemd timer. Then there's also event-based updates with the bootc fetch apply updates service, which can be triggered. And lastly, it can be manually updated by running bootc upgrade and rebooting the system. So, and in case something goes wrong with the update, bootc is capable of rolling back to the previous working image. And you use the bootc rollback command for that. So for more details, you can check out this upstream documentation, which is linked here, continuous.github.io/bootc. All right. So how do you, I need to give you more time to do the demo. How do you actually build a container? You can use existing tools, like I mentioned, and then with that, you can then customize the image as you need and build the image with the specifications that you list. So you can use any existing bootc-based image and customize it to your needs. And for more details, again, the link is here in Fedora docs, building containers. All right, at the moment there are 3 distros with bootable containers, Fedora, CentOS Stream, and RHEL. So I will not, you can see the Fedora and CentOS base images here in the link, but I will now hand it over to Cedric because I think he has more interesting demos coming up to show you how these applies to AI workloads.
That's a perfect segue, and I think we have just a second to kind of check this out as well. So here, also in the slides and everything, is where you can actually take a look at the base images and understand what they actually contain. So you've got full image philosophy, where you've got the kernel, systemd, network manager, a lot of other utilities, and then you have these little minimal images that is really just the base. If you think about it with the UBI images for RHEL, for example, you've got the minimal, you've got the regular, you have one specific for packages, and you could actually create your own base images for bootable containers. So if we go to the source, Fedora, oops. If we go to source for the actual code here, CentOS 9, we can actually understand in the container file how we're creating these base images. So if you want to take a look at that and kind of understand how you could create your own, for example, please do. All the code is here linked in the slides and also from the Fedora documentation. But let me hop back over to the slides and let's talk and see how we actually relate this to AI workloads, which is what I do every day at Red Hat, doing AI specialty tasks and working with customers to get their applications from POCs to actual production, whether it's on an OS like RHEL or CentOS or something like that, or in the cloud, for example, with Kubernetes. So the recommended use cases for bootable containers. A lot of these are pretty standard and you would actually expect this. So for example, one-to-one with the app and host. Most organizations, this is how they do everything, is they're setting up a virtual machine, running one application on it. The benefit for bootable containers here is that you can stack everything at build time so that you have less drift, and so you can actually minimize errors before things go into production, because sometimes the app team is a little far away from the OS team. We can also think about edge appliances, so if something is an IoT device and doesn't regularly get updates, well, we could just use bootc so that whenever it does have connection, it pulls down from the repository that update. But for me specifically, what I love and I'm very interested in, both of us here, is the AI ML stack. And this is a new kind of concept that we've had to think about because we're running all AI workloads essentially now on Linux, right? So to be able to perfectly version the app dependencies, kernel dependencies, the GPU, accelerator drivers, CUDA, and everything else into one stack is really, really important. And so you can kind of see a quick little demonstration of this here. Because in these little bullets, most of the world is already leveraging containers for AI workloads. You can think of NVIDIA's NIMs, for example, and a lot of other use cases. And having this kind of in a bootable container allows us to run the AI models as close as possible to the hardware, so that's benefits in latency, speed, cost, etc. And we're actually going to show an example of this with a RAG demo. But this is a huge opportunity. This is how we're actually building Red Hat Enterprise Linux AI, which is essentially using bootable containers to stack the different components on top of that base image. So you've got the component for the model fine-tuning and training, right? You've got a component for the model serving. You've got a component for just various other utilities that come with this appliance. And so this allows us to version these dependencies in a way that makes things much less complex. So you think about stuff like PyTorch, right? If we go back to this diagram, I'll go back one step here. You could have, for example, PyTorch, and then VLLM, and then the AI model on top. So having one standardized way to put everything together is really, really useful, and it makes a lot of sense. So we're actually going to see this, and the biggest part is that build time versus patching in production is really important to be able to have this stability. But let's see this in action. We've got 5.5 minutes here. So just as we would use containers to do all of these processes in a CI/CD pipeline, and don't forget security, for our applications, we're going to do it for our operating system with the bootc utility for Podman Desktop. How many of us here use Podman Desktop or Podman? Sweet. Okay, that's like at least half the room. So if you haven't seen it before, in the catalog, there's an extension that's going to make your life really easy when you want to build disk images from your containers. So what you do is essentially you would build an image just like you would through the regular process. This could be done with Docker, for example. using a boot C base image, so Fedora CentOS rel. And once that's built, we actually convert that into a disk image. So you can use one of those options. So for example, a Amazon disk image, virtualization guest image, a .raw, whatever you would like to deploy, and you wait about 2 to 5 minutes, and you've got that, and you can launch that as a virtual machine. So 4.5 minutes, let's go ahead and see it. Yeah, sure. So the first part that we're going to do is the first half of the demo, which is test and experiment with an AI application. This is, as an application developer, the first stage that everyone's going to go through is like, hey, we've got a use case. We want to use an AI model. How do we actually do that? And can we do that from our local machine versus use a third-party API where we're sending our data? Maybe that's confidential data, or maybe we just want to keep things local. So shall we? Yep. Cool. So over here, Podman Desktop, my favorite tool for working with containers. I wasn't paid to say that. We're here at the recipe catalog, and so there's a lot of utilities to work with AI in containers here, but what we're actually going to do is set up a recipe. So this includes all of the different, I guess I could say, ingredients to set up an AI application. So for example, we check out the code from GitHub, we copy a model as a volume into a container. That inference server is Llama C++, but you could use VLLM, which is a production-ready serving runtime. We build a vector database as a container, a front end, and we package everything up in a pod. So if I go over here, we can see that all the containers are running together, and let's open up the application, and let's ask a question. So who's keynoting FOSDEM 2025? So this model, all right. Demo effect. Here's what I'm going to do. I'm going to restart it, and all those steps that you saw earlier are just going to be recreated, right? That's the beauty of containers. I can easily shut something down and easily start something back again. And fingers crossed, we're not going to get a strange error. But the question I'm going to ask is something that the model wasn't trained on, right? That's the purpose of RAG, is to pull in external information that the model doesn't already know about. Fingers crossed. Come on. Hold on. All right. Oh, okay. Okay, we'll try it one last time. If not, I'll just skip to the bootable containers part. So let's see. I'm just going to delete all of these guys. Everything was working before I got here. So that's the beauty of the live demo. So we'll start the process again. If I wanted to, I could just download a model from the catalog and run that there, but this allows me to pull in source code and actually build an application that I could start experimenting from. Fingers crossed. Hey, who? Maybe I didn't like my question. Who keynoting FOSDEM 25? Okay, so the model's going to think about it. It doesn't know and it can't answer. We're going to provide some information here. This is a FOSDEM brochure that I generated in text. And we're going to upload that in a vector database, and we're going to ask the question again once it has processed and chunked that information, and we'll be able to determine with similarity scores if that context is relevant and pull that back in. So when we ask the question, we got 1 minute left. Okay, we're going to go fast. We're going to ask that question again. It's going to have the context and be able to pull in all the information for the question that our person is asking, right? So great little use case of RAG. What we're going to do actually is come over here and open up the source code. And here we have it. So we've got the container file to build that application, and we've got the source code in Python to actually have that front end and make the calls to the model that was running locally. In that same repository, we've got a container file that is going to build the bootable container. So it's based on CentOS Stream 9, and we're pulling in, for example, the model. We're pulling in the inference server and the database there. And we're setting that up and essentially going to start that as a service, a systemd service, when we actually build this. And so I kind of ran this all here earlier. I'll run it again. Well, all right. Pretend I didn't do that. We've ran this and tagged it locally so that if I go over here, I can check out my images. 4 seconds left. Whew. RAG. Okay, well, let's see. Now we have it in our image registry here locally on our machine. It's quite a big image, but think about it. We're including the model, the inference server, everything that it needs, so that we can now, I'll show you this last part, build this and put it into whatever disk image type. And then finally, we could even run it as a virtual machine, and this is what I did earlier, so that we could test this application out locally and now take this and put it to wherever we want to deploy it. But I went a little bit over time, and I'm really sorry, so we'll kind of wrap up here. And thanks, everyone, for your attention. I hope you had fun.